Hello, and welcome to Video AAPT, a virtual workshop series run in partnership with Physics Today. I'm Mike Hall, Director of Membership for the American Association of Physics Teachers. Before we begin, let's go over a few housekeeping items. At the bottom of your screen, there's a floating menu bar with shortcuts to the tools for engaging with this workshop. These are resizable and movable, so you're welcome to move around and get the most out of your monitor space. At the far left of the bottom toolbar is the media player control for viewing the speaker. During the second half of this workshop, you might want to maximize that frame. I'll be monitoring questions submitted in the Ask Questions frame. Please help us make this virtual workshop interactive by submitting questions throughout the event. We'll try to answer these questions during the event, but if we're unable to, we'll answer your question via email. You can expand the slide frame by clicking the arrows in the top right corner. There are also links to websites with more information about planning for upcoming solar eclipses and eclipse viewing strategies included in the related content frame. Some networks cause slides to advance more slowly than others, so we recommend logging off your VPN. Also, please close any programs or unnecessary browser tabs that could cause issues. You can find answers to common technical issues in the Help tool at the bottom of your screen, or reach out through the Ask Questions frame. A recording of the event will be available after the event concludes and can be accessed using the same audience link that was sent to you earlier. Episode 1 is sponsored by AAPT partner Digitalis Education Solutions, and it is a pleasure to introduce Dave Cuomo, Education Specialist at Digitalis.
Hello, everyone. Thank you very much for joining us for this inaugural episode of Video AAPT. We at Digitalis are very excited to be hosting it. We are a company that makes planetariums. We make planetarium software, planetary systems, and portable planetariums. So we're really excited to be able to bring you the Eclipse today. And as Mike said, we want this to be interactive. If we were in a planetarium together, I might walk over, sit down next to you, and hand you the controls and let you fly the planetarium for a little while. I can't do that here. So please go ahead and ask questions. Type those questions into the chat. We don't mind being interrupted. In fact, in some ways, we're hoping for it. I'm here in Western Washington, Western Washington State, where Digitalis Education Solutions is headquartered. And I'm going to send it over to a colleague of mine, Richard Gelderman, who is currently in Western Kentucky. And Richard, please.
All right, Dave, thanks. So I agree with Dave that we are asking you to interrupt us. Mike will look at the questions. Since Mike knows the types of things we're going to say, if he recognizes that it will be addressed later, it may be that he just puts you off. So questions about eclipse glasses being safe, for instance, will get put off till when they fit in a handful of slides from now. So I'm so serious about asking you questions, you asking me questions, that I'm going to ask you questions. So this is a multiple choice. Total solar eclipse is something I have, and please answer from your point of view. A, B, or C? So I've got a thing that tells me what fraction of the people have responded. I'm not going to go for 100%. I might do that in a classroom, but I'm not going to do it with you all. But we're barely crossing 50%. And so please go ahead and fill out this. It gives me an idea of what you're going to be looking at. Okay, so we're past 2/3. I'm going to go ahead and click through. And now the results are up. And this isn't a surprise to me, but it gives me an idea who you are. In really round numbers, I see basically a quarter have never seen a total solar eclipse, and that another quarter have seen more than one, and that about half of the group has seen one and only one. I'm going to, because a full quarter is a meaningful number to me, talk about some things about the basics of eclipses But what I want you to know is that on your screen, in the resources tab that you can get to from that bottom floating menu bar, there are a whole lot of things that are labeled according to my annotation of what I think that link does. So best overall Eclipse site is greatamericaneclipse.com. It doesn't say that, but click on those. And if you have never seen an eclipse, that will give you a good idea about what to expect and how to plan for it better. Those are not going to be the strong points that Dave and I cover. Instead, we're going to spend most of our time talking about how to do classroom activities related to the eclipse, not the details of the coming eclipses themselves. So a total eclipse is a human experience. And a lot of my fellow astronomers don't get this when all they know is the textbook answer to an eclipse and why it occurs until you see one. And when you see one, you recognize it's not science. It's not about geometry. It's not about mathematics. It is a purely human experience. It overwhelms your senses. An eclipse is one of those things that will not fail to live up to expectation. And when you see it, it, of course, overwhelms your sight because it gets dark in the middle of the day. In the middle of the day, the sun disappears. That's just incredible. Until you've seen a total solar eclipse, you've seen nothing like your body's reaction to the sun disappearing in the middle of the day. But more than that, you can feel a total eclipse. If you lacked the power of sight entirely, then you could feel the temperature drop. You would feel a total eclipse. It's more than just sight. And even more than that, if I wrapped you up in a thermal blanket and you couldn't feel it and you couldn't see it, while an eclipse doesn't make any noise, nature changes. Everything around you will sound different during the eclipse. I could tell you that an eclipse is happening just based on the sounds of what's going on. And for starters, if you've got other people around, the moment totality comes, people tend to scream. So one of the things that I'm going to urge is really to help your community be part of this celestial wonder. It will not fail to disappoint. So here's another poll for you. I want to know, for the total solar eclipse that is coming on Monday, the 8th of April, 2024, in a couple months, where do you plan on being? I didn't actually say I live within the path of totality and I plan on staying there. I just assume that's going to be true. I think it would be silly. Ooh, Renata. Is this poll not showing? Something went wrong. Okay, it is showing. I take that back. Thank you, guys. I see the answers are coming in now. Thank you. It was stalled on my end, probably. So almost 50% of you have answered. I'm going to wait until we get past the 2/3 mark, headed towards 3/4. So this is going to be something that I want to encourage you to do, but boy, I understand all the things. So live in the path of totality. I assume you're going to stay there. Some people might say I'm renting my house and I'm getting out of there, but I assume, and then we'll travel to the path of totality. Given this self-selected audience, that doesn't surprise me. And so that's 65% right there, almost 2/3. We'll view the eclipse from outside the path of totality. There is stuff that is just going to make it so that folks can't get into totality, but I'll talk briefly about that. And then the last thing, there's still a little bit more than 1/8 of you are saying, I don't know where the path of totality will be. That's not the emphasis of what we're going to talk about. However, at the end, if you hang around, we can deal with your questions and help you understand where the path of totality will be and give you all of the resources and point out the links that are available there on the website. So here is what I've got. And I got the numbers. I just saw who you are and where you plan on being. But just in case I could change anyone's mind, it never fails to live up to its expectation. Yes, there is weather and people have jobs. It is a Monday, the 8th of April. If you're a teacher, then you've got classes and you've got to decide. But my rule that I tell people when they ask is anybody outside the path of totality should get into the path of totality. And what I say to teachers especially is to teachers, do not confuse 99%, even 99.5% with 100%. The difference between full totality when the sun disappears in the middle of the day and 99 or 99.5% is everything. It's the difference between twilight and night. It's the difference between night and day. So never, ever give up when you just get close. Oh, I'm 98. Isn't that good enough? I'm 99. 99.9. Walk that extra mile. Get into the path of totality. My next rule is going to be, once you're inside the path of totality, let it go. Quit worrying about things. Don't fret the details. Once you are inside the path of totality, it's just a matter of how long the sun will stay disappeared, and just let it go. You cross the path of totality, you get a couple 100 yards in, and you're going to get tens of seconds. That will not be enough. If you are where the eclipse is the longest, it will be about 4.5 minutes. That is not enough. And so one way or the other, it's not going to be enough. You wish it lasted longer. Once you get in the path of totality, just stay there.
Hey, Richard.
So, yes.
Just a quick question. Is there do we have in our links a map that shows the totality path in the U.S. for the April?
In the links we do. We have a number of different links. Okay. I tried to annotate them with words that I would find descriptive, but there are places where you can put in your location on a Google map, and it will tell you exactly what you've got. So my thing is, if you are 100 miles from the path, spend your time between now and April to arrange a field trip. My call is, and you can ignore me because if you can't, you can't, but the difference between 99.5% and 100% full totality is the difference between night and day. It is not, wow, well, it's 99%. Isn't that good enough? It is not. And I don't have that slide. It's in the links. But the amount of light is different by factors of hundreds. The amount of light that's still around when you're 99.5%, and the difference between that and totality is night and day. If you are close, do what it takes to get in there. If you have to leave your students behind, then it's a decision you make. Your duty to your students versus your duty to yourself. This is a remarkable experience. On one hand, if you can't treat yourself well enough to see it, then what are you going to treat yourself to? Don't stay close and think it's good enough. Okay, so I want to go ahead now and I want to start talking about what you'd want to do and what you'd want your students to do. And going back to the fact that it's a life-changing experience and it overwhelms your senses, I really, really don't recommend that you come up with a whole lot of plans where you decide that you're going to take data and do a bunch of things. Just enjoy it. And I beg of you, please do not assign to your students a bunch of tasks to accomplish during totality. When it's partial leading up to totality, sure, go for it. After totality, it tends to be very anticlimactic. They got all the time in the world. Have them take care of business after totality, but during totality, the only thing I'd have you worry about taking pictures of is each other. Take pictures of the crowd. That's the one that's so totally amazing. So take pictures of the crowd, not of the eclipse. You'll find better pictures of the eclipse on the web, and you'll be able to look at them and say, oh, wow, that's what I saw, or that's even better than what I saw. But pictures of the crowd, that's what you'll want to see when the eclipse is over. That's what you'll want to see that night. And when you talk about it with friends, that's what you'll want to show the next day. That's what you'll want to go back to the next year or 10 years later, is how it changed you personally. It's a human experience. So, observing the eclipse. If you tell your students, don't look at the sun or you'll go blind, which I'm sure is something we've all heard before, you tell your students that, you're lying to them. Think about it. Everyone here has at some point had the sun in their eyes. You have looked at the sun, and I would bet good money none of those here have looked at the sun and gone blind because of it. What is true is don't stare at the sun. One of the dangers of an eclipse is it's interesting, and you've certainly been told it's interesting, and so you'll want to stare at the partial phases, and mind over matter, you could hurt your eyes. The chance of going blind right then is pretty small, but if you stare at the sun, you will do irreversible damage to your eyes. That is still a simple enough message to tell your students. Don't challenge them with something that isn't true. They'll call you on it, and they'll delight in proving you wrong. Of course, the sun can get in your eyes and you won't be blind. But don't stare at the sun. And if you stare at the sun, you will do irreversible damage to your eyes. So the corollary on this is unfortunately one that many of the administrators in the district offices in Kentucky in 2017 wanted to repeat over and over again is, oh, don't look at a solar eclipse or you'll go blind. And for starters, it's just the sun with the moon in front of it. Soon as the partial phases start, there's just less light than there was before. There's not more. The big thing is there are no dangerous eclipse rays. Now, an ophthalmologist will be happy to tell you, and I will repeat based on their authority, that when the amount of light goes down as the moon is crossing in front of the sun, your pupils are going to dilate. They're going to get a little bit bigger because there's less light. When they dilate, then the dangerous ultraviolet and infrared rays are going to be able to go ahead and get into your pupil very easily, and that can do damage. I am not saying don't look to look at a partial eclipse. I'm just saying that there's nothing more dangerous about the sun when it's being eclipsed partially than there is with the sun when it's not being eclipsed partially. So don't stare at the sun is still a truth. And what happens if you do, you will do irreversible damage to your eyes.
Richard, a couple of questions. This might be a good time to answer the question from earlier about how can you tell if glasses that say they're safe for an eclipse are actually safe? And there's a second question from Carrie, who wants to know, why isn't the path of totality the same for every eclipse?
Okay, we will get to the second question here in a bit. And eclipse glasses for these things much at all. And one of the things I don't like is, why would you want to hook something over your ears? When you have these on, you are blind. There's nothing you can see through these. They're not sunglasses. They are blocking 999,999 parts out of a million. They're only letting 1/1,000,000th of the light through. So why would you want these hooked over your ears, a partial eclipse is a little bit like watching paint dry. It takes hours for the eclipse to get first touched by the moon until it's fully covered, and then to unwind again to more than 2 hours. So you're not going to be wearing these like you wear sunglasses. You're only going to put them on to see, and that's why I personally like these cards, which then means I'm not calling them eclipse glasses. Instead, they're filters, and the filters, the solar viewers, which is one name for them, they are great things. Now, the polymer filter that makes these does 3 things that you care about. It effectively blocks 100% of the infrared light, and that heat light is dangerous to you. It effectively blocks 100% of the ultraviolet light, the same light that's causing skin cancer, the UVA, UVB rays. And it's blocking 999,999 parts out of a million, only letting through 1 part in a million of the visible light. This polymer, as long as you can hold it up to your eyes, and even with the brightest light, you can't see a thing, it has totally blinded you. You're looking through it and absolutely nothing is visible to you, then you're okay. If it's got scratches or punctures and you can see any light through it for anything other than the sun, then you're in trouble and you need a new set of them. Trina asks the question that also could go to infrared and ultraviolet light. In 2017, what I say here, the sale of unsafe counterfeit solar viewers, people got things that were shiny mylar that cut out a lot of the visible light, but not the ultraviolet and not the infrared. And boy, even a physics lab is not likely to have the spectrophotometer to be able to measure that. On the back are codes that assure you that it's safe. But if I'm going to sell you counterfeit viewers, I'm going to counterfeit the code too. So why can you trust that? So the polymer filters, plastic polymers, the polymer filters are going to block the infrared and ultraviolet, and that is hard to test for. So then the only thing that's left for me is if you've got them and you're worried that they are letting through ultraviolet and infrared, it's really hard to test and I can't give you an easy answer. If you don't have them and you're going to acquire them, I would suggest getting them from one of the 2 largest and most reputable firms, both in the United States, Rainbow Symphony and American Paper Optics. Go to those places and get them. Don't go for deals. Don't get them off of unknown people in Amazon. Don't get them direct from China. There are other people who can sell you actual quality solar viewers, and I apologize to them, but for the sake of a crowd, I'd say most of the filters out there, 95, 96% of the filters out there are made and sold by Rainbow Symphony and American Paper Optics, and go with them. So I'm going to skip past this because I've spent time talking about other things, and I'm going to say really quickly that my bias is do not look through telescopes, not because I've never looked at the sun through a telescope, not because maybe you haven't, maybe you have, and you've done it safely before and you can do it safely again. My call is, in a session about classroom activities related to the solar eclipse, is I'm saying that if you've got a telescope and it's got something shiny on the top, then other people are going to look at that, not hear your words, not understand the concerns. They're going to go get the family telescope out from the closet, they're going to put a shiny Mylar balloon over the top and they're going to think it's okay. And they're not going to understand why their eyes are damaged. So I would say looking at the solar eclipse through a telescope isn't going to be that big an advantage, and it's not worth the risk. So the next very safest thing would be pinhole projection, and the trouble with pinhole projection is twofold. On one hand, you've got a little hole through a piece of paper. The sun is shining through that piece of paper, and it's projecting an image of the sun down below. But it's counterintuitive. People go to look at the sun. They don't want to look 180 degrees away from the sun. And so there are people, no matter how many times you tell them what to do, they put this piece of paper with the pinhole in front of their eyes and stare through the pinhole up at the sun. And now they're staring at the sun. And that was the big no-no that we agreed it wasn't cool. So one thing is this, this thing where you've got a piece of glass. The piece of glass is on a ball. And now the ball is just on a cylinder. On the left-hand side, it's on a piece of masking tape, a packing tape. And on the right-hand side, I've got this little piece of PVC cylinder. And you can point it at the sun and then shine it at the place where you want it to go. So I've got a poll for you. You see, this is two examples, the white one here and the pink one. You see the two differences? So here's a question for you. Which mirror on a ball created the image of the sun in the middle? The image of the sun in the middle was a little bit distorted, but it was a nice round image. Which one of those was created? Which one of those created what you see? I'm not seeing the poll numbers come through. And so I'm going to go ahead, for the sake of time, I'm going to go ahead and click through here. I'm not quite sure how many people looked through. And so here we've got on the right, on the left, numbers not too different, and either a slightly bigger number than that. And what I want to point out is this was a square mirror. They just put a circular aperture through. This was a square mirror. And the answer is either would have created this. So here is the penultimate thing that I want to say. The NASA Punch mission has created the 3-hole punch pinhole projector. And what it's got is a square hole, a circular hole, and a triangular hole on the same card. When you've got that card just fingertips away from the wall, the light that's coming through creates, from the square hole, a square image of light, from the round hole, a round image of light, from the triangular hole, a triangular image of light. But when you get not fingertips away, but arm's lengths away, then what you see are circular holes for all. And that's the trick with the pinhole projector. So if I click through here, this URL, punch.space.swri, Southwest Research Institute, .edu/pinhole.php, gives you a fantastic set of lesson plans to go through this, to look at the sun now before the eclipse is ever there. I'm not going to go through this in detail, but they give you indoor activities. If you're limited and you don't have windows or the ability to get outside, they give you in-class activities, and they let you understand the question that goes like that mirror. So if you're doing observing in the classroom, what I truly encourage you to do is you want to create situations where they're thinking about it. An eclipse is a motivating experience. It's going to catch their attention. So now it's up to you as an instructor to get them involved in the investigation, coming up with the prediction, running tests or experiments, and iterating. So here's my example. This is a picture, and someone asked, for this October the 14th, Saturday, October the 14th, annular solar eclipse. I've really been talking about total solar eclipses before then. Here is the path of the annular solar eclipse. You can see that the eclipse shadow is crossing into Oregon, off the Pacific Ocean onto Oregon at about 9:15 Pacific time, 11:15 Central time. 5 minutes later, it's crossed through Oregon and is down into Nevada. These are all from greatamericaneclipse.com. 5 minutes after that, it's down near the Four Corners area. 5 minutes after that, it's solidly in the middle of New Mexico. 5 minutes after that, excuse me, I clicked through Texas. And then 5 minutes after that, crossing over San Antonio. And 5 minutes after that, it went from 9:15 to 9:50 Pacific time. It's leaving Corpus Christi and going out into the Gulf of Mexico. So here's my question to you. With luck, you've got a pop-up window on your screen, and the poll should have popped up a separate window with a text box. And the text box is asking you to write down a question about something you see in this sequence. So here is the last slide of that sequence to help remind you of the types of things that were there. Now that poll window is movable, and that poll window you can drag to the side so that you can both enter text and see the slide at the same time. It's going to be up there for about 20, 25 more seconds. So if you put your cursor onto the poll window, you can drag it to the side, still enter. Now there's over 160 of you there. I'm looking at the results. I'm trying to get through the results really quick, and I'm entering some of those into, excuse me, as I multitask, into a slide. Okay. So here's some of the more common questions. What is a question you could come up with? And my point is, an eclipse is motivating, an eclipse is inspiring, and so let your students come up with the questions. Instead of you telling them what the questions are, let them come up with the questions. What determines the width of that black dot or the yellow stripe? Why isn't the path purely east-west? There was a question that Carrie asked about the direction of the path, and that's it right there, right? Why isn't the path purely east-west? Why does it go at an angle? Why do other eclipse paths go in different directions? Where are the ends? The high speed, why isn't the speed constant? So let me now go to April's eclipse and click through it. Here, the eclipse path is in a different direction, but notice it's still starting on the west side of the screen and moving to the east, which is related to one of the questions that I copied down there. Here it is just off the coast of Mexico at 12 o'clock. Here it's 20 minutes later. 20 minutes later, it's starting to cross into the US, about 1:30 Central Time. 20 minutes later again, it's now in the middle of Texas over Dallas-Fort Worth. 20 minutes later, Arkansas, Oklahoma. 20 minutes later, it's in my neck of the woods. It's in southern Illinois, the edge of Missouri, western Kentucky. 20 minutes later, it's solidly in Ohio, not far from the man who said that that he was 100 miles away from totality in Detroit. 20 miles later, it's crossing Niagara Falls. It's going to run right up the border of New York and New England and Canada. Now it's up near the edge of Maine, and now it's up in the Maritime provinces. It started at about 12 o'clock Mountain Time. An hour and 40 minutes later, it's crossing into the Maritime provinces and off into the Atlantic. And so ask them the questions. And one question that we'll pick on is why. We'll take Carrie, she put it in the question and answer, why from west to east. And my thing is, from the Earth point of view, you can convince people why the globe of the Earth, if that's America, why the globe of the Earth as it rotates, why we call east and west, and that the sun appears to rise in the east and set in the west. Well, you can do the same thing for the moon. Here's an observing activity that I set up for students on the 19th of September, on the 20th of September, on the 21st. I drew on this sheet of paper what my horizon looks like. A set of big pine trees, a factory with smokestacks, a bunch of telephone poles, a steeple, some other big trees of different type. And I also drew what some of the stars looked like at that time in the evening. And I can show that the moon is moving from the west to the east. So I can establish that while the sun moves from east to west, the moon, with respect to the background stars, is moving from west to east. And that starts to explain why the eclipse starts on the west coast and moves to the east. Maybe southwest to northeast, maybe northwest to southeast, but it always is from west to east. So I am limited here with two-dimensionality, and we're going to turn it over to Dave. And Dave Cuomo, with his planetarium, is going to guide us through a better three-dimensional understanding of how to work classroom activities that deal with the meaning of eclipses. It's all
right. Hey, thank you, everybody. Wherever you are, I'd like you to give a good, nice round of applause for Richard. Richard did a great job, and I think set the tone for what we want to do. We want to get you set up to be excited about the eclipse. And hopefully, I'm going to be able to answer that question that Richard left off on. Why is the moon moving west to east? And also give you a sense of what you might experience in an eclipse. First of all, up in the top right of your monitor in your computer, in your window, of your browser window, there'll be one of those square buttons with the arrows going out in four corners to expand into a full screen. You should make my image a nice full screen image, because that way you can see my planetarium. And what I'm going to be doing is presenting through my planetarium here and not giving you slides, but showing you through the planetarium system here. And this is my planetarium. What we're looking at here is kind of what we call the all sky view. Imagine you're lying on your back in a big meadow looking at the sky, and you can see the forest around you, and at the center, just above your head, is the zenith. You could also, of course, stand up. You could stand up and then turn around and pan around so that you can see from the south to the west, the north, the east, and then back to the south. So sometimes I'll be using this view of the sky to show you what we're talking about. And then other times I might be giving you, well, this view through my spaceship window here that we can go ahead and take a look. And right now I'm flying us out into space a little bit so that we can see the eclipse passing across North America. And I'm bringing us to a point just above Durango, Mexico, which is where the totality will be the longest of the entire path of the eclipse. And I noticed in the chat a little earlier, somebody said, well, if I'm just 100 miles from the eclipse, it'll be fine. I can be here. And no, 99% of an eclipse is not a total eclipse. Even 1% of the sun is too bright to look at. As a matter of fact, Pluto, the dwarf planet, the ice planet, however you want to call it, it is 4 billion miles, almost 6 billion kilometers away from the sun. And if you could stand on Pluto and look at the sun with your unaided eye from there, it would still be too bright to look at. So there's no substitute for totality. And now let's take a look here. So let's get ourselves oriented. I've got my little mouse here so I can point things out for you. That's the totality circle there. That is the shadow of the moon. And we're going to take a look at that. And we're going to go ahead. And right now, I'm going to park us in what we call a geosynchronous orbit, or a Clark orbit for some people. It's a position that stays exactly above the same part of the planet Earth. So I'm going to keep us right here above Durango, Mexico. I'm going to get my mouse out of the way. I'm going to use the right mouse. And let's go ahead and watch the eclipse from space from this perspective. And there it's going. It's going from southwest to northeast. It absolutely is. We can see it passing into Texas there, soon passing into Louisiana and Arkansas, and then into Richard's neck of the woods into Kentucky, soon passing into southern Illinois. You can see it passing there south of Lake Michigan, into Ohio, and up to the maritime provinces of Canada, where it will leave the North America. So we just watched it from space, staying over Durango, Mexico. But of course, everything's moving in space. The sun is spinning around and it's moving around the center of the Milky Way galaxy. The Earth is moving around the sun. The moon is moving around the Earth. The Earth is rotating 24 hours or once every 24 hours. The moon is rotating once every 28 days. Everything's moving. So let's put some things into play here as we start looking at it. Same starting point. We're going to look at the eclipse starting in Mexico just after it's crossed into Mexico from the Pacific Ocean. But now we're going to let the Earth rotate beneath us. And as it does, we're going to be moving closer or further into the Pacific Ocean. You can see we're now over the Sea of Cortez and Baja California. We're crossing over about the time that it gets to Richard. We're well off Baja California. And we're going to see it like that. So it's moving across the Earth in that path. And each eclipse is different. And we can maybe show you a little of that if we have some time later. Let's go a little bit further out into space to really put this into perspective. And this is something that we now, those of us who teach in the 21st century, have the advantage of having had people go into space, having sent spacecraft into outer space to study things. Speaking of spacecraft, the Punch mission is a really cool mission that Richard mentioned. It's actually 4 satellites, 4 solar orbiting satellites, each mini satellites, each about, they could fit on my desk. They could fit on my desk, and its mission is to study the corona and how the solar corona, which we're actually going to take a look at here in a minute, creates the solar wind. Okay, let me put some things into perspective for you. First of all, everything is bigger. The Earth is now 20 times bigger than it really is. The moon is 20 times bigger than it really is. They're not this close together. This green line, that's a shadow. That represents the shadow from the moon to the Earth. And of course, shadow that the Earth is casting off into space as well. And this is the orbit of the moon. So we'll go ahead and I'm going to advance time again. This time I'm going to advance more than the 4 hours that it's going to take, 4.5 hours that it's going to take the eclipse to go from Mexico to Canada. I'm going to go about a week into the future. So we really get a sense of what's going on when we're looking at these planets. Okay, so we can see everything's moving counterclockwise, at least from our perspective above the North Pole of the Earth. Everything is moving counterclockwise. The moon is moving counterclockwise this way. The shadow is moving off with the moon. The Earth is rotating counterclockwise. And we'll stop here in, about 9 more seconds. And then we'll take a look at why, when you go out night to night to night, is the moon moving from west to east, even though it rises in the east and sets in the west. What is that all about? It's a matter of perspective, really. So here we are. Let's imagine that you are here and you are looking at the moon. You're looking at the moon here. So I'm gonna put my mouse right there by where the moon is. And imagine you're looking at the moon from that position on Earth. And let's just jump ahead one day.
Hey, Richard, if I may, a question came in.
I'm sorry, what's that?
Yeah, go ahead. Just came in. Why is everything moving counterclockwise?
That's an excellent question. And I'm sure as physics teachers, as science educators, you all know one of the most important things to be able to say to your students, to each other, to ourselves, is I don't know. And I don't know why everything is moving clockwise, and some things aren't. Neptune has a moon Titan that is actually moving the opposite direction. Some of Jupiter's moons are also moving the opposite direction. But why it seems that everything is moving counterclockwise from this perspective, I don't know. Maybe one of your students can find out. And Venus also rotates in a clockwise motion, although it orbits counterclockwise. Great question, and thank you, because it does give me the opportunity to remind all of us that when a student hears their teacher, hears an authority figure say, I don't know, let's find out, that alone can be a very, very inspiring moment for a student. And also lets the student know that science is more than a collection of facts, but is a process of finding out what we can know and finding the evidence. Let's go ahead. Thank you. That's a great question. Let's go ahead and move further out. Move further out into space. Oh, we're actually moving back to the original. I pressed the wrong button. It happens sometimes. We'll press the right button in a moment. That was the right button. So what I want to do is I want to position us so that we can see the Earth, the moon, and the sun. I also want to position us so that the moon and the Earth are in their actual sizes, not that blown up version that I was looking at a moment ago. And there it is, there's the moon. 30 Earth diameters away from the Earth. It's pretty far away, actually. It's considerably further away than Mars's 2 moons, Phobos and Deimos. And here's the shadow, and there's the Earth, and then the shadow of the Earth. And this, of course, is the orbit of the moon. I'm going to see if I can get a glance at the time. Oh, we're doing fine. So I want to position us behind the moon so we can fly back off to the Earth and get us to a position that we can then land in the middle of the eclipse so we can see what that experience is like, because it is an experience, and it's an experience like, well, you won't have another experience like it. And I want you, when you're there, when you're looking at the eclipse, imagine you as a physics teacher, you as a citizen of the 21st century, know the Earth is round and know the moon is passing in front of the sun and know that it's not a dragon eating the sun. But that's a relatively new phenomenon that so many of us know this thing. It wasn't long ago, not that many generations, when people didn't know that, when people did not know things that we just take for granted. And there are some people who still don't understand how we know that the Earth is round, or that the distance between the Earth and the sun, how can we measure that? How can we know what the sun is made of? So imagine as you're in the eclipse and the sky gets darker and darker, and nocturnal animals start to stir because the sky is getting darker. Their diurnal clock is going to be adjusted and they're going to start acting. You'll start hearing nocturnal birds singing. The temperature will drop. If you are someplace with a very long totality, it might get cold enough that you start out the eclipse with a clear sky, and by the time it ends, there's clouds, especially if you're near a coast or a marine layer. As the temperature drops, you could get some clouds building up. You'll also see, and in this eclipse, you'll see all of the planets, the visible planets, visible to the human eye, will be visible in the sky, in the daytime sky. But when the moon goes away, or when the sun is blocked by the moon, you'll be able to see Mars and Saturn, Venus, Mercury and Jupiter. The further west or the further east you are on the path of the eclipse, Mars and Saturn, as you can see, they're pretty low in the horizon here in Mexico. A little east on the eclipse, they might be below the horizon by the time you get to totality. And then there's that corona. And the corona is the atmosphere of the sun, and it's 1,000,000 degrees Fahrenheit. It's hotter than the surface of the sun. And that's another one of those I don't know moments, because we don't fully understand why the corona is so much hotter than the surface. That's one of the things the Punch mission that Richard was referring to is going to investigate. And we also won't know what the corona is going to be like until you're at totality. It will depend on the atmospheric conditions of where you are. It will also depend on the atmospheric conditions on the moon. And unless you are at 100% totality, you're not going to see the corona. So if you can get to totality, I do urge and encourage you to try to get there. And as we watch the sun come back out of the mouth of the dragon that tried to eat it, and see the crescent sun as the moon moves off of it, enter questions into the chat, and I think we'll have a little bit of time for some questions. And thank you very much for spending your evening with Digitalis Education Solutions, with Richard, with Mike, and with the AAPT first webinar. So thank you very much. And Mike, why don't I hand it back to you, but let's go ahead and look and see if there are any questions that we can answer.
Thank you, Dave.
Thank you.
there are a couple of responses regarding the counterclockwise motions, and I'm not
Oh,
sure if others can
that's
see.
great.
Can you see those?
Yeah, I can
Dave?
see that. I can see that. And thank you for answering that. And it's absolutely right. If you go back, the Earth or the solar system formed out of a cloud of dust and gas. That dust and gas started to collapse. As it did, the hydrogen in the center of that dust and collapse started to spin around. It started to get hot, and that rotation that it took on at the time it was collapsing and spinning, just kind of like a figure skater pulling their arms in and spinning faster. As that rotation got started, that is the rotation that was imparted on the solar system. Why it went counterclockwise instead of clockwise? There were probably gravitational reasons for that, but I don't know them. Thank you very much for reminding me of that answer.
There is another question. Can you explain again the apparent west-east motion of the moon?
Can I explain again the apparent west-east motion of the moon? Yes, I can. And let me do that from this perspective. Let me go ahead, and I'm going to go ahead and try to find us a time when the moon is in the sky. So I'm going to just jump. There's the moon. Okay, I jumped a week into the future. There is the moon in the sky. And we are right now, we're still in Mexico. We're still at Durango, Mexico. It is April 15th of 2024. Let's see what happens when we're looking at the moon from Earth and we jump a day into the future. As we jump into the future, we'll see that the moon is moving from west to the east. If we go out at the same time every night to look at it, we're going from west to east. So yes, as we see the moon going across the sky, it rises in the east and sets in the west. We're familiar with this. We're familiar with the sun doing this. Of course, the sun moves and not the earth. I can see it. Well, that's a whole other webinar. But the Galileo webinar, my favorite subject. Okay. But if we look from night to night, from day to day, and we look at it, we'll see, because the moon is rotating in that direction, the moon's actually moving this way, even though the planet's rotating this way. And Richard, correct me if I'm describing this incorrectly. And that's why it appears to move from west to east. Excellent question.
All right, I think this question will be for both Richard and Dave. The question is mountaintop, desert plain, or grassy field. Which place would you pick and why?
Dave, if you want to pick one, I'll pick another one.
I would look at the weather, the climate forecasts for those particular places in April, and what they are. A mountaintop, as I said, you've got thinner atmosphere. As the temperature drops, you're going to see a faster temperature drop. So I would depend on a number of factors. What would you say, Richard?
So my call for the plus for the desert is, right, it's a desert for a reason, no clouds, better
Right.
weather here. My call for the mountaintop would be getting to see the shadow come, getting that elevation from a mountaintop and watching that shadow swoop over you. You can see this, that some people have captured on YouTube videos. It's available, but a YouTube video just doesn't capture the grandeur the way it is. So to be on a mountain and have that shadow coming up is an amazing thing. To be on the grasslands is a whole separate thing, since I've in Kentucky, we're kind of at the start of the Midwest, and the grasslands are starting to dominate bluegrass country and all that. It seems like home to me, and it feels like a good, comfortable place to be. And so I could give a good reason for any of them. And my call really is just get to the path of totality wherever you can. And once you're in the path of totality, stop sweating the small stuff and enjoy yourself.
And I'm going to quickly answer a question in that someone is asking, do I mean the revolution of the hydrogen and the dust in the nebula as opposed to the rotation? And yes, I do.
Yeah, orbit, spin, revolution, rotation, unfortunate choice of words. Mike, I want to pick up Steve's question. Steve asked a good question about the 99.5% of a total eclipse isn't a shorter eclipse. That's how much the moon is covering the sun at maximum. And so 99.5 means there will always be a sliver of the sun visible, that it never gets dark. So it's not shorter. That happens with whether you're on the edge of totality or you're in the center line of totality. 99.5 is the coverage, and it means there will always be 0.5% of the sun visible. And since the sun is so many millions of times brighter than everything else, even 0.5% of something that's millions of times brighter is still really, 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 really bright. And so that's why you want to get into totality, not say, oh, I'm 99%, isn't that close enough?
Great, thank you.
So Dave is zooming in on a circular shadow, and of course at the edge of that circular shadow, that's where just a little bit of the moon is glancing across you. It's fully covered just for a shorter amount of time, and the longest would be through the middle of that circular shadow.
Yeah, I was going to see if by just changing a degree of latitude of my positioning, I can demonstrate the difference between I moved 1 degree and we no longer are at totality. And if I were to zoom in, there's going to be a speck of light coming from it. And if it's not a planetarium, it's going to be bright enough to hurt.
Yeah, that contrast is hard to show. So I want to pick up another question, Dave, that I think I misread before. I didn't quite get correctly. Why isn't the path of totality the same for every eclipse? And it's going to do with the seasons and the tilt of the Earth, as the Earth is orbiting the sun and the moon is orbiting the Earth, where the nodes, the line where the moon and the sun line up, where that happens with respect to the tilted Earth. But mostly, what I would say is that why isn't the path of totality the same for every eclipse is the kind of question your students will come up with. And so don't worry about coming up with a short, snappy answer for your students. Instead, worry about how to design an investigation so that you can get them looking up data from old eclipses and figuring out patterns for spring eclipses versus patterns for summer eclipses versus patterns for fall eclipses, and see those directions themselves, and then be able to answer that question themselves based on observations looking at the data. It is an excellent question. Let your students ask it. Let your students answer it.
That's right. And it's related to why we don't have an eclipse every new moon and why we don't have a lunar eclipse every full moon. And it's related to the angles of the orbits. This blue line, this long one, represents the angle of the Earth's orbit around the sun, whereas this one represents the angle of the moon's orbit around the Earth. And if we go a month into the future, we're going to see that I did not have this properly set up, so I'm going to make you dizzy. By the way, if you'd like to become dizzy, I can totally give you that power. I totally have that power. Let me go ahead and there we go. Sorry about that. I apologize. We went from one new moon to the next, and here we can see that now the shadows are not lining up. We had over 800 people to our school for a 4-hour event in August. This year, we have the event right after school. We have fun activities for students from K through high school. We expect more people this year, assuming we have good weather. Any recommendations to make sure we manage the safety issues with...
Something went wrong. Please try again.
So my call on that, Paul, is the thing that I put up when I talked about telescopes is never have a magnified image of the sun in direct line to your eye. Don't trust any filters, don't do anything. That's one safety recommendation. And the other is we found during transits of Venus, transits of Mercury, or partial eclipses, is that people really are safe in general, and that in a crowd, the safety tends to gain precedent instead of rambunctious maverick behavior. People kind of calm each other down. And so having solar viewers available, even if everyone doesn't have one, people will share them. And that people will look out for each other and say, hey, maybe you shouldn't be doing that. So I truly believe that as long as you don't have magnified images of sunlight around, that the amount of pain that it causes one when their eyes start watering and they start blinking to look at the sun, combined with the availability of eclipse glasses, I think that you're doing okay. And I think the fact that you had 800 people for 4 hours, you're set. And so, yes, a whole bunch from Paper Optics, you order them in bulk and they cost you less than $1 a piece. And then it's easy to either give them away or to find a sponsor so that you can give them away. So I agree totally.
Yeah. I agree. And you can also, if you're able to have facilitators out in the field with people, because the eclipse is going to take a while, you're going to be watching the sun get smaller and smaller for a couple hours. And while you're doing that, you can have people perhaps setting up exhibits where you've got a beach ball to represent the Earth, and then a ball that is half or a quarter of the size of the beach ball to represent the moon. And you could have people guess, here, take the moon. I'm going to stay here with the sun or with the Earth. Where do you think the moon would be? How far away? And demonstrate how far away the moon is and why at that distance it's able to cover the disk of the sun. You can have facilitators out working the crowd and talking with people.
So I want to really quickly say that Mark, who asks about planets of Mercury and Venus, if after Dave's presentation where he showed that all 5 of the naked eye visible planets can be viewed during totality, if that's not good, get back to us, because I think that Dave covered that. And I want to say that Joel's question about precession. Precession is a mismatch between orbital spin and other forces, in this case, the gravitational force between the Earth and the Moon or the Earth and the Sun. And the spin of the Moon is already slow enough, and the gravitational pull where we've got the tidal locking, that precession is going to be something in astronomical geological timescales, but not in timescales of human history. So the precession of the moon's orbit around the Earth is not an important factor during our human history of observing the heavens and having records of observed the heavens. It's not that it's not true in geologic or astronomical timescales, just not like we can see precession with its 26,000 year period. Jonathan gave great reasons about the why the counterclockwise motion tells us something about the nature of the solar system, and that if you find something that has a counter rotation, you're almost certain that something odd caused it. And he mentions collisions can cause counter rotations. And then says demo with a sheet of spandex, a heavy ball in the center, and that gravitational stuff is incredible. I thought about being able to demonstrate that, because I think it's one of the most powerful demonstrations I've seen in the last 5 years, where all marbles go in all directions, and yet after just seconds, there's marbles that have been kicked out, marbles that have fallen into the middle, but any marbles that remain end up orbiting in fairly circular orbits in the same direction. Sometimes it'll be clockwise, sometimes it'll be counterclockwise, but they all end up orbiting in the same direction in fairly circular orbits. And that demo is incredibly powerful, and you can find YouTube videos on the net if you can't create a spandex thing that's big enough in your classroom. And then I see suggestions from people ordering glasses, and then Thousand Oaks was mentioned as a source of solar viewers, and Thousand Oaks certainly is an amateur astronomer where we get our filters, and they are definitely a supplier. And then other suggestions about activities for different age groups. But given that it's already 12 after, I think that that's all the questions. I appreciate the comments and the suggestions, but I think we're giving it back to you, Mike.
Okay. Thank you, Dave and Richard. At this time, we're going to conclude the workshop. Very special thank you to our series co-producer, Physics Today, and to our episode 1 sponsor, Digitalis Education Solutions. Please be on the lookout. Probably in the next hour or so, you'll get an email with a survey link. We hope you'll take a moment to complete the survey to help us make this the best workshop series it can be. Also, please do check out aapt.org/video for information on episode 2, which we hope to announce soon. So thank you all for attending, and have a great night.
Thank you all.